everybody, let's talk about separating a mixture of compounds today. If our goal is to separate a mixture of compounds, we actually have a whole variety of ways that we can go about doing this, but all of them ultimately come back to differences in physical properties. And this really means it's all about intermolecular forces. So we're making those connections as we're going both in this video and in class. We're going to talk about 4 different ways to do separations. There are more, but these are 4 nice ways to do separations. So we are going to talk about chromatography, filtration, extraction, and distillation. Now, the first 3 of these are all based on either solubility or polarity, while distillation is based on differences in boiling point. We're going to take a brief look at the theory behind each of these, and we'll do several of these in class so you can kind of experience this process. There's lots of experimental details that as we see these and as you come across them in lab, that it's important to learn, but I want you to make sure you have a core understanding of how these different separation processes work today. Let's start with chromatography. So there are lots of different kinds of chromatography: thin layer chromatography, gas chromatography, liquid chromatography. We're going to talk about paper chromatography. And as you might guess from the name, paper chromatography means you have a piece of paper involved. In all types of chromatography, you have what's called a stationary phase and a mobile phase. The stationary phase is some material that doesn't move. And then the mobile phase is going to be a second material that does. And what allows the separation of your components is a differential attraction to those 2 different materials. So we're going to talk about paper chromatography here today, but understand you can generalize this to the other types of chromatography. So in paper chromatography, your stationary phase is a piece of paper. And this piece of paper is going to be placed in a mobile phase, which is some solvent, often water, sometimes something non-polar, maybe like, or less polar, like acetone, or ethanol or methanol, some sort of solvent that's going to serve as your mobile phase. And what happens is you put a dot or a spot of the mixture of components that you want to separate where it is towards the bottom of this piece of paper, but above the bulk mobile phase, the bulk solvent, in a sealed container. And as time passes, in this sealed container, the liquid, the mobile phase, is going to be drawn up the paper. Well, as that happens, once it reaches where your spot of mixture is, then the components of your mixture are going to end up being either adhered to the piece of paper or dissolved in the solvent. And the relative amount of time that each of those components spends either in the mobile phase or on the stationary phase will determine how far up the piece of paper that it travels. So something that is, say, very soluble in the mobile phase will spend most of its time in the mobile phase and will travel a long distance up the piece of paper and say end up towards the top of the piece of paper when you are done with your chromatography run. Whereas something that is not as soluble in the mobile phase but is more attracted to the stationary phase won't travel as far up the piece of paper. And thus we see a separation between these 2 materials. We can talk about something called the retention factor, which is a way of telling someone whether a material in your mixture is more attracted to the mobile phase or the stationary phase. And your retention factor is a ratio. It's the distance that your compound of interest traveled divided by the total distance that the solvent traveled. So in my image up above, I can measure the distance that was traveled from where I spotted it up to where, say, this red compound ended up, and that'll be the numerator. And then I can divide that by the distance that the solvent traveled, which will generally be noticeably farther. And so I'm going to get a value between 0 and 1. And the greater the attraction based upon intermolecular forces for the mobile phase relative to the stationary phase, the greater the retention factor or RF value will be. And so chromatography is a nice way to separate compounds based on their intermolecular forces. Filtration is going to use solubility, which again is based on intermolecular forces. And so in this case, if we have, say, a mixture of two solids, and I will call them A and B here. If I have a mixture of these two solids, I will add a solvent, whether that's water or something else, that only one of those two is soluble in. That leaves one as a solid and one dissolved up in the liquid. And so at this point, then I can pour this through some sort of filtration setup, whether that's gravity filtration or vacuum filtration, which you'll be doing in lab for me before too long. And that will leave the solid on the filter paper, and whatever was dissolved will then be found in the filtrate. That's the liquid that passes through that filter paper. And then if we want to obtain whatever material is in that liquid, we can just evaporate the solvent off, and then we'll have our two materials. And so filtration is a familiar separation technique that we can use if things have differences in solubility. A third technique is extraction. And here again, we are looking for differences in solubility. But now, instead of trying to have one material remain a solid while the other dissolves, we're actually going to look at partitioning our mixture into two different liquids. One, it will be more polar, and one will be less polar. So for this one, let's consider that we have a container, and I felt like drawing a round bottom flask, so you get a round bottom flask. And in this liquid, I have a mixture of component A and component B. We're going to add a second solvent with a different polarity. So maybe this was water, so I'll add something like hexanes, which is nonpolar. And the key here is that one material will be more polar and soluble in the more polar solvent, and one is less polar and will be soluble in the less polar solvent. And then all we need to do is separate these two layers. Now, when you go to add that second solvent, you do have to shake to make sure that you have an ample opportunity for both chemical A and B, in this case, to come into contact with both the polar and nonpolar phase, so that you can actually have that separation occur. But then what we'll do is we'll remove and separate those two layers. And the easiest way to do this is with something called a separatory funnel. And a separatory funnel, or sep funnel as we like to call it, is super convenient. It has a stopcock at the bottom, so you can drain off that lower layer, and the hourglass or teardrop shape of it helps you really get a nice clean break between the two different layers. So separatory funnels are wonderful for doing this kind of extraction process. The fourth of the separation techniques we're going to talk about is distillation. And this one is a separation based on boiling point. And so let's say we have a mixture of two different liquids. One is lower boiling than the other, which means as we start to heat it up, the vapor above the liquid is going to have a significantly greater proportion of that lower boiling material. It's going to have weaker intermolecular forces. At any particular temperature, there'll be more of it in the vapor phase. And so we're going to have a vapor that is enriched in the lower boiling component. And so what we'll do is we'll heat it up, and as that vapor rises, we're going to put it through a distillation column. There's lots of different variations that can help improve your purity to make sure that you're really getting just one component at a time through the distillation process. We'll leave that conversation to a time when we really need it. But the idea is that you take this vapor as it is heating up and you start recollecting it. And so you're going to put it through what's called a condenser over here. And there's different kinds of condensers, but water condensers are kind of the classic, which basically has an exterior jacket of water around a glass tube on the inside. And that keeps it cool so that the hot vapors then recondense and deliver your purified liquid into a receiving flask of some kind. So as you start heating this up, what you'll see happen is the temperature is going to rise, and then again, the vapor above the liquid then will be enriched in the lower boiling component. And then once you reach the boiling point of that lower boiling component, your temperature will actually plateau. And that's the boiling point of that lower boiling component. And as long as you're at that temperature, the heat that you're putting in is going into overcoming the intermolecular forces in that lower boiling component. And so you'll see a plateau, and you are monitoring the temperature of the vapor, not the bulk liquid, but the temperature of the vapor. And you'll see a plateau in that temperature. And so you can know what it is you're collecting in the condenser at that time. And then once all of that lower boiling, or the vast majority of that lower boiling component has been removed, you'll tell, because the temperature will start to shoot up again and rise until you reach the boiling point of your higher boiling component, where again you'll hit a plateau. And so distillation is a really nice way. If you have two more volatile liquids, you can separate them based upon their boiling points. So at this point in time, we've talked about chromatography, filtration, extraction, and distillation. All of these are ways to separate a mixture of components. All of these depend in some form or fashion on intermolecular forces, whether that's relative attraction to a polar and more nonpolar liquid, whether that's ability to dissolve, or whether that's boiling point. We have different ways to separate our materials that really leverage those differences in intermolecular forces, which of course are reflective of differences in the molecular structure.